Okay, go ahead, my friend.
Okay. Hi. Yay. I'm Fernanda Romo. I'm a student from Tecnológico de Monterrey, and I'm going to present you a project called Neutrino Classification Through Deep Learning. I developed it to obtain the Master in Computer Science. And, well, basically, the objective of the project was to apply deep learning to classify neutrino events, employing the pattern they generate, where the radiation, the chunk of radiation that is generated. Since this pattern can be given as input to deep learning algorithms as inputs that can be processed by these algorithms precisely. So for example, I show as an image or as a cloud of points. And this project was proposed in order to precisely identify the particles in the event before the reconstruction. And in, in general, it was to determine which works best. So about the data, it was simulated. It corresponds to the intermediate water Cherenkov detector, which is a smaller tank than Hyperkamiokande, which is currently being built in Japan, and is being developed to aid in the Hyperkamiokande functioning. It's 8 meters tall, 10 meters diameter, and contains 536 multi-PMTs. At the moment, this was simulated because more or less the design has been changing as the project evolves. All data is of single ring events. This means it's just one particle per event. And we have three classes, gamma, electron, and muon. And I basically worked in two supercomputing clusters. One is CATS, located in Universidad de Guadalajara, and the other one is CEDAR, part of the Digital Alliance Research of Canada. And the number of events varies in each dataset. And this is of importance because, as we will see later in the results, the larger the number of events, the better the results we got. And in general, I applied for deep learning architectures. I list them there. Three of them are CNN-based, which means we can give as input tensor of certain height, width, and number of channels. And for pointed, we use a representation of 3 dimensions. So we have the data, it is simulated, then we convert it to an appropriate format, as I mentioned, and then we process it. This can be optional. We apply that augmentation, double cover. Double cover is a, how can I explain? It's a transformation that is applied to the event so that we have twice the information of an event in just one single image. And the final part is about filtering the images depending on the number of pixels different from 0. We applied a methodology based in computer vision. And this was done because there are events that we had that had sparse hits, and these greatly affect the classification when the datasets were small. But as we found later, the greater the dataset, then this is not a problem anymore. So we stopped doing the images filtering, but it actually kind of works. But we must mention that by eliminating these images, we eliminated events of certain energy. And these provided biased models to certain range of energy. So we stopped using it altogether. And then we applied the training, validation, and testing recursively so that we could tune the hyperparameters of the architectures. And as output, we obtained different metrics. They are all applied for different parts of the process, but in general, the ones that we used at the end for comparison among themselves and with state-of-the-art methods were the ROC curve, is receiver operating characteristic curve, and the area under set curve, and the efficiency, as well as a plot of efficiency and the area under the curve. So that's an example of sparse heat events. So smaller the dataset, the greatly disaffected. And in general, we obtained 9 models. As we can see, we had high hopes for the model called Vision Transformer because it's a higher complexity model, but it actually gave the poorest results. So that's why we tried a lot of things to make it work, as we can see here. And one of those was to separate the data from muon and not muon, and then the not muon class as electron and gamma. And yeah, so that's basically it. And my results. So I present you the row curves. A row curve, ideally, for the best model we could get of a row curve will be one that from the beginning goes to 1 and has an error under the curve of 1. And the worst kind of model we could get was one that it's really close to the dot line, which means we have a model that is kind of guessing between classes. I show you the curves per each class against the other two. And as we can see, well, I don't know if you can see it, but in all curves, as we can see also in the electron that is in the next slide, the best model was ResNet 50, used with the greatest data set. And the one that gave the worst results was Vision Transformer, which gave an error under the curve greater than 0.5, which could be the worst model, but still it didn't get better than that. And this is the electron. And as we can see, the ResNet 50 with Cedar dataset is the best. And I here show you an efficiency plot. I consider the electron class as signal and the gamma class as background. So we try to find the one that rejects better electron from gamma. And as we can see, also the best model was ResNet 50 with the Cedar dataset, which was the largest. And this value was especially computed because we are comparing with the values obtained by the Hypercamicande collaboration. And as I can show you in my conclusions, the ResNet 50 model provides the best results while also consuming the less computational resources. BGG19 and Pointed, when we're compared with this model, actually gave more or less similar results, but it took considerably longer, like 2 times, 3 times the time needed for ResNet 50. ResNet 50 gave the greatest error under the curve for all applications in comparison with all the other models. And well, we computed also the efficiency for all the models, for all the classes. And where one model could give really good results for gamma, it was really bad for electron and vice versa. But ResNet 50 actually managed to be stable across those two classes specifically. And Vision Transformer gave the poorest results, but in a way it was to be expected because Vision Transformer needs to be trained with the largest dataset possible. So it actually improved by using a pre-trained model, but not that much. And in Watchmal, which is the part of the Hypercamicande collaboration that does the analysis with machine learning, they had an error under the curve of 0.71 and 0.77, but this was not by analyzing the results as they were. They made cuts to the results, and I didn't apply them. So I have a more or less similar result, but to better compare them, I will need to make those cuts. And in general, the more data we use, the better the results. And for future work, I consider that it will be important that we make sure that actually ResNet 50 was the best. So there are other models that perform, they function on the same principle of ResNet 50, like DenseNet or InceptionNet. So I think it's important to test them. And if possible, to train BGG and Pointed with the largest dataset, even though that will take a really, really long time. And train Vision Transformer from scratch. Vision Transformer needs a pre-training and then a training. So the pre-training part was done using a dataset called ImageNet, but this dataset contains classes like dogs and cats and things like that. So it will be important to train it from scratch with the largest dataset possible. There are other transformer models such as BAIT, which will be interesting to try. And I didn't try traditional machine learning techniques, but I thought it would be important, remarking that the difference is that in traditional machine learning, we have to extract features from the data and then we train and test a classifier. And with all of these that we made, we are working in a paper. And that's it. Thank you for your attention.
Okay, thank you, Maria Fernanda, for your presentation and on time. Thank you very much for respect the time. Okay, questions to Maria Fernanda? Yes.
Thank you for your talk. In your slide number 3, please.
Yep.
It's actually 2 questions. Can you explain a little bit your classes? You have 3 types of classes, and these events are are independent of each other? Or you don't see this events mix in the same, let's say, if you have one particle that is entering the detector,
Mhm.
you are trying to discriminate these three classes in this one event, or you have three different types of events.
Okay, so in this class, more like in this specific case, since I only have single ring events, then it will only be one of each class at a time.
Mhm.
There are also multi-ring classes, so it can happen that we have more than one at a time. And these are the three classes in specific because it's like the most type of events that we are expecting.
And on second question, please.
Mhm.
Can you give a basic idea of what are the features you are trying to extract from these classes? Because each type of particle will generate some time of response in the detector. So, what are the characteristics between that difference each one?
Mhm. So in deep learning, we don't extract features. Actually, the architecture extracts the features for us. So what happens in a deep learning architecture is that the first layers extract the features and the last layers classify them. So since we're using convolutional-based architectures, what is done is that a kernel passes through the tensor and extracts features from it, like, for example, changes from light to dark or things like that.
Yeah, but you have to have a. I understand that the network is doing the work.
Mhm.
You are not saying the network how to do the work.
Mhm.
The network is learning.
Yep.
But you have, it's my opinion. You have to have the idea of what is the process that is differentiating these classes. You have to have what is the characteristic that I think is in principle you have to have an idea of what is
You mean
making
like in each different feature map that is being extracted, what is inside of it? Oh, okay, okay, okay. Is the heat charge of the event. Yeah. Okay.
Okay,
Yeah, sorry.
okay.
Right. When you train those classes, uh, you train with labeled data, right? And then you use uh the deep learning algorithm to then classify, right? Because you feed it first. That is that correct?
Yes.
Okay.
But well, yeah, your question was what was inside those images, right?
Yeah, no,
Yeah, it's a charge.
it's this is more for example, I don't know about the hyperchemical. I don't work in hyperchemical, but if I apply this to air shower experiment, we know that, for example, one type of shower has some characteristics that differentiate this from other types of
Okay.
shower. So
Yeah.
that's my question.
So in Muon class, actually these are higher energetic. They are like larger rings with greater number of hits.
Mm.
And precisely the problem that we have with gamma and electron is to tell them apart because they are really similar. Muon has a lot of energy, but electron and gamma are smaller rings, but they kind of look similar sometimes.
Okay, thank you.
Yep.
Okay, thank you very much for your talk. So now
I have another question. Sorry. If it's okay. Oh, you were asking. Sorry. Sorry. Yeah. So you said you're doing your work for IWCD.
Mhm.
Uh, are in your plans to take your analysis to the part detector? I mean, how difficult will it be to take what you have for the part detector?
Oh, okay.
Mm.
So it depends on the, well, no, sorry. It's actually, if I recall correctly, the data is kind of in the same format as this one. So the process will be to actually convert that data into an input that can be processed by the deep learning architectures. And obviously they had to be tuned too, because yeah, the tune we did to these all the models that we got was specific for this kind of data.
Okay, so I have several questions. So the firstly, the which energy that you are using for these samples for the gamma and the electron and the muons?
Yep.
Uh,
For all of them, the events can range from 0 to 100 MEV, I think. Yeah.
So, but in the IWCD, so that the energy is a bit higher actually. That is better to use realistic energy region for the optimization. And another other question is how about the performance? The ring is produced near to the corner of this cylinder shape.
Yeah. Actually, it's a really good question because we actually had trouble with that. We made several plots in which we analyzed in terms of the distance from where the event happened to the walls in the direction of travel of the particle and the closest distance to where the event happened. And the problem was that the distribution of data didn't have a pattern at all. Like it sometimes provided a ring, sometimes it didn't. And that was precisely kind of the problem.
Thank you very much.
Okay, another question? Okay, if not, let's thanks Maria Fernanda
Thank you.
again. Okay, so with this we finish this afternoon session. So see you tomorrow here at same hall, same channel, same time, and enjoy the dinner. And see you tomorrow. And thanks to all the speakers again.